All right, so let's get going with today's session. Please put yourself on mute if you're not speaking. I can put you on mute from the server, but if I do that, you will not be able to unmute yourself.
Okay.
All right, so when you're speaking, you can unmute and then you can continue, right? That's probably the best way to deal with it. All right, so what we will be doing today is essentially going through the 4 questions that we had. The theme for this week is app, and it's just like we just picked a random theme and we're going to get going. So the first question that we have is the first app is essentially aggregation of prime permutations. So the goal here is essentially to, given any number, input number, you are expected to make a permutation of that, and then like you don't have to use all the digits, and what you do is that if any of the permutation is prime, you just keep adding all of them. So if you take 1, 2, 3 as example, the output is 72 because 2, 3, 13, 23 and 31 are prime, right? So, Kavit, what was your choice? How did you do it?
Okay. So initially in my approach, like how I generally do is I have taken an upper limit of 10 raised to power 5. Like I can increase that upper limit as well, but for now it's 10 raised to power 5. And then till 10 raised to power 5, how many prime numbers are there? I have pre-computed it and saved it in a vector list with a flag with 0 and 1. So 0 means it's not prime and 1 means prime. Then I have done a brute force of suppose the number is 1, 2, 3. So I ran a recursive function that performs the combination of all the numbers. So if I pass in 1, 2, 3 to it, it will generate 1, 2, 3. So these are the 3 numbers. Then it will generate 1, 2, 2, 3, 1, 3, and then it will generate 1, 2, 3. So I get all the combinations of 1, 2, 3, that digit. Now what I do, I have this saved in a vector list. Now I iterate through that vector list. So when I get 1, and I run another method that does the permutation of the number. So in case of 1, 2, and 3, the individual numbers, the permutation will be same. Now the case comes when it's 1 and 2 is passed. So the permutation could be 2, 1. That's it. So that way, my functions calculates that, and I keep on saving this all in a set. So what it does, suppose my number is 212. So in that case, one combination would be like 2, 1, and another combination can again be 1, 2. So 1, 2 will have a permutation as 2, 1. So because 2, 1 has already been computed, it's unique. So I don't run the function again. So it helps me to reduce the iteration cycles basically. So now once I have these all numbers, because I have pre-computed the prime numbers, I just need to check whether the flag is 0 or 1. It takes O of 1 time, and I keep on adding it to
you're actually leveraging the pre-compute, right? So there are 2 distinct approaches that I've seen, and I'm trying to see which one is better than what, right? So 2 things is, one is actually to one approach is to you generate the permutations first.
Okay.
And then you check for prime, right?
Okay. Yeah, that could be
the other approach is actually to generate the prime numbers.
Yeah, generate the prime numbers.
And then you check for permutation.
Yes.
Because is like 3 a permutation of 1, 2, 3? Yes. Is 31 a permutation of 1, 2, 3? Yes. How do you know that? Because I need 1, 3 and 1, 1, and you have 1, 3 and 1, 1 in your input, right?
Okay.
Yeah. So checking for permutation is not super hard.
Yes.
Okay. Now checking for generating the prime numbers is anyway an activity you're doing, right? So you could potentially generate like the largest number that's possible.
Okay. Yeah.
Generate the largest number how do you generate the largest number possible?
Yeah, so so if I have a number input as 1, 2, 3, I sort the digits and form a number, so it will be 3 to 1. Yeah.
Correct.
So if my higher upper limit is 3 to 1, then I calculate all the prime numbers before that?
You calculate all the prime numbers up to 3 to 1 and then you check for permutation. So that's also a way of doing it. And unfortunately there is no easy way to actually figure out which is actually more effective and which is less effective.
Yes.
The reason and the reason is like to do the generation of the prime numbers you can use the sieve, right?
Yeah, I use a sieve, but then you send a link about the Miller-Rabin one also. I have used that. Yeah, I've used that. I've used that once also, but like generally in competitive competitions they give you the upper limit, so I prefer using sieve. So,
right.
yeah.
So you can use the sieve and you can actually use the sieve up to the prime number. So you just do the generate first and then you can check for the permutation afterwards, and that kind of works.
Yeah.
Right?
Yeah, I did the other way around, generating the permutations first and then kind of checking whether it's prime or not.
You can do both approaches. Either approaches are fine, but I think depending on the data set that you have, one is better than the other. Like if the input number that I give you is like 999999999, right? Okay, maybe like 100 times, like 10 digits or something like that. Then the permutations are actually very simple.
Yes, the permutation.
Okay, and I mean in this case everything will be a multiple of 9, so it doesn't work. But let's say if I give you, whatever the thing is, right? If I actually give you multiple duplicates, then the way it will end up working is that you will actually generating a permutation will be better because you'll only be generating like a handful of permutations.
Yes, because unique sets of permutations.
Correct.
Will be
correct. And then maybe, and anyway if you're using the Miller-Rabin way of generating the prime, the checking the prime, that's faster as well.
Yeah, that's faster because the set is like 4 or 5 elements and then checking the primality test.
It's much easier, right?
Yeah,
so that is the solution. So both solutions work. I did not know about Miller-Rabin before this. Somebody just brought it up in the chat, and I looked it up. Looks like a pretty neat way, and it's fairly accurate from what I can tell.
Yeah, it's fairly accurate. It's probabilistics, but still, it has given good results all the time.
Yep. So that was good.
Guys, a quick question. What is sieve you guys were talking about?
Can you explain, Kavit? What is sieve?
Yeah, so sieve is like what happens, I'll explain you in terms of coding only. So suppose I take I is equal to 2, right? Now I know 2 is prime. So what I do, I run another loop from 2 to suppose 1000, and all the multiples of 2 I mark them as visited. So what happens when my next time the loop comes I equal to 4, I'll see it has already been visited, and if it is visited, that means it has a factor other than 1. So that means it's not a prime. Got it.
So it's like looking forward and marking.
Yeah, looking forward. Yeah, so basically it reduces your cycle because you won't be going again to 4 or 6 or 8 such kind of numbers.
So this is a way to generate sequential prime numbers fast.
Yeah.
So here's I'm just looking at the Wikipedia article. So this is the method. So if you start with 2, you mark out all the even numbers, like how Kavit was saying. Then you start with 3 and you mark out all the multiples of 3. So then you start with 5. You pick the next one, just mark out all the multiples. Pick the next one, mark out all the multiples, and so on. So it's actually a pretty fast way of figuring out because you've eliminated most of the numbers anyways.
Yeah, I like the reverse approach for this problem. You discussed the reverse approach that start with generating all the primes and then check if they are a permutation
or not. So I think the crux of this problem is not about, see, these are all like why I like this problem. I mean, I don't think I have seen this problem anywhere. I just
even I have not seen this kind of.
Well, I made this up, so I highly doubt it's like it was. I didn't pick it up from anywhere, but I wouldn't be surprised if the same problem exists already somewhere, right? So it's not a brilliant problem, but why I like this problem is that there are 2 ways to look at it. Like I'm asking you to get an intersection of 2 sets, right?
Yes.
One is prime, the other one is permutation among the number sets. So which means that you can always go from one set and try to filter the other set, or you can start from the second set and try to check for membership in set 1. Now, which one makes more sense entirely depends upon the situation that you have.
Situation. Yeah.
Right? And
Yeah.
it also depends on the check, how fast is your check and how fast is your membership generation. So whenever you are dealing with a problem space of where you are trying to compare between two different broad areas, you are trying, this is what comes in. So I did not know that the Miller-Rabin thing actually kind of messed with it. Otherwise, in general, the second function is usually better. Like, you can generate all the prime numbers up to the largest one using the sieve, and then you just check for permutation. That's the fastest way of doing it, and that is not the intuitive way as how I expect people to think of. So that's what my angle was when I was creating this question. And then some wise guy walks in and says, "Here is Miller-Rabin," and I learned it. It's an interesting way, so which is good, right? I like it.
Yeah.
You always learn something every day, right? So I like it.
Yeah.
So that's the deal. The sieve of, I think it's called like Erythros, whatever that name is.
Of Erythros, I don't remember the spelling. Don't ask.
I have it I have posted it in the Etherpad in case you are looking for it.
Okay.
Okay, so it's there. So yeah. So that is this question. So it's a pretty straightforward question. It's not complicated, but I think the only takeaway that I want you guys to have is that you should definitely think of, there is always two ways to look at it. You go from one to another or the backwards, and in many cases, like whether it is a depth first search, breadth first search kind of a problem, sometimes it's much easier to actually go from the end and back, and that's pretty much like the thing to remember in this case. Right?
Yeah, that's why I liked your second problem, because for second problem you gave the solution and it was like spot on.
So
like doing the reverse.
So let's talk about let's pivot to this. Any questions on the aggregation of prime permutations?
Yeah, there is one more thing I want to add. I think in the forward path, generating all the permutation and then checking for prime. I took that path, but I trimmed down some branches where to speed up the permutation. That okay, if the number ends in 2, don't need to check, and if it is divisible by 3, then don't need to check for the whole prime. Otherwise, check for if it's a prime.
No, but okay, how do you check for something as a prime? You divide by 2, check, and then check. Divide by 3 and then check, which is exactly what you've done anyways, right?
Yes. Yeah, that's
so
right.
That doesn't say that, but here is a smart way of doing it. So when you're generating the permutations, right, don't generate from first digit to last digit. Generate from last digit to first digit. When you do that, like for example 1, 2, 3, right, you don't have to consider any number ending in 2.
Yes. Yes. Yeah.
So you can ignore the entire tree. You don't have to. So if the last digit is divisible by 2, then don't bother. If the last digit is divisible by 5, is it 5 or 0? Then don't bother. If the last 2 digits are divisible by 4, then don't bother. If the last 3 digits are divisible by 8, then don't bother, and so on. Right? That's pretty much what you can do to cut your permutations big time.
Big time.
That's what I was doing. I was checking the last digit, and at every step, that last digit is 2 or 5 or like divisible by 2, last digit, then don't check. Yeah, I think, but yeah, last 2 digits, last 3 digits, I think that idea can be extended. Yeah.
It's an extension of that. But you can't do divisibility by 3, unfortunately, because divisibility by 3 requires the entire number to be generated. And that doesn't really save much. Yeah. Because once you have the entire number, you are dividing it by 2 and you're dividing it by 3 anyway. So that's the first 2 things you check. So it's not, that won't help.
Yes.
Right. So that's like the thing. So there are tricks that you can actually employ there, but it's more around how you are logically organizing this. Okay.
Yeah.
Right.
All right. So let's go to the next one. All right. So I think this next one is also a fantastic question. I like it. Yeah. I have used this question in the past, and this question is actually from it's a shamelessly copied from an NPR show called Wait, Don't Tell Me. No, this is a Way with Words. NPR show called Way with Words. And in that, there is this guy who comes in. He comes and provides puzzles. So he was providing a puzzle with the word app, but in his example, the app will always come together. It's always A, P, and P. So hen and happen were examples that he was using. So I extended it to make it like the app will have to come in sequence, but not necessarily in not necessarily together, like how toadies and toad pipes, right?
Yeah.
It doesn't change the complexity by a whole lot, but it actually makes an interesting spin. So I didn't see a whole lot of solutions for this. Did people post solutions?
Yeah, I posted it, I posted the REPL link. I don't remember where I posted it.
Yeah, I think you did. I saw one or two. Yeah, my apologies. Actually, this week has been a little heavy, so I haven't been able to follow through. But it's good.
Yeah,
so
I take the try solution for that. So build a forward try and keep checking partial check. But that was based on permutation, generate permutation, and see if the forward permutation is partially matching or not.
No, okay. Because can you like restate what you're saying?
So if we start with a smaller word, and for every step of the way, so we put all the words in a try, and we pick up a candidate word, see if adding app into it will match another existing word. So every step of the recursion, we look forward by one step and see if you're in state 1, we look for a forward A. And if there's a forward A, we took that branch for free so we took that branch for free and then keep matching rest of the word.
Got it. That might work. I think but it's a little more arduous.
Yeah.
It is more expensive. Yeah.
So
much easier.
Yeah, the reverse is so much easier, right? So this is like an interesting test case as well. So it's much easier to actually start looking at it saying all the words. If you are going from word A to word B, right? What is the property of word B? It contains the letters A and P in succession, not necessarily immediately after each other, but A followed by some letters, maybe P followed by some letters P, right? So if you want to like use regular expressions, then this actually contains A dot star P dot star P, right? It should match this, correct?
Yes.
Yes.
So first thing you do is you filter it. Filter your output, your set B is only words that contain this, which only that matches this.
Mm-hmm.
Then what is the next step? Then the next step is what?
Next step. Yeah. So I did what you suggested to go in a reverse way. So what I did, So I took a string app, okay, app, and I took an index as 0. So when I go into recursion, I check that okay, string. Obviously, the string has app. The another string happens, suppose, and then I remove a from it. So now what it becomes HPPEN, and then for the next cycle, I send this string HPPEN with index +1. So the index +1 is for the P thing in the another string that I am sending as a parameter. So the next cycle, what will happen? The next available P will be removed. So now the string becomes HPEN and my index becomes +2. So my base conditions becomes like if my index reaches the app end, app's end, so return true. That means okay, this word has been found and it's been reached. Otherwise, the recursion goes on, and to minimize this, I am saving the state using an array. So whenever I reach some partial state and it has been like suppose, because there is a list of words text right in the GitHub link. So suppose already something like if I have a word like to do, TODO, and that to do had given me false. So if this to do comes as a partial in some other word, no, that is not a correct thing. Yeah, that I should remove.
Actually, I'll think more on the try solution which I was doing originally. That may actually be better.
No, wait up for the try solution 1 second, because we'll come back to the try solution, right? So set solution is this, right? The only exception, the only extra piece that I want to talk about is you can remove the APP, but there is a possibility that you may actually have multiple A's and multiple P's, right?
Yeah. So that doesn't matter because I am removing it in order APP. So in this case, one A will be removed, one P will be removed, and then another P will be removed. So that's fine.
So let us assume that your word was this.
Yeah, and after my function call on this method, my string will become AB. So then what I check, if AB is contained in the existing list, that means okay. If I append app to AB, there will be a word that.
Yeah, but what about BA? If BA were to be the dictionary, you're good, right?
Got it. So wait. So in this case,
you would actually be matching BA, not AB.
Yeah,
because you will take the first A, right?
Yes.
You will only manage this. You will not match this.
Yes.
Right.
Yeah.
So that is the thing to figure out. And there's also maybe there is more P's as well, right? It could be this. Right?
Yeah, that's true now. Yeah, because my thing would only check for BA.
Correct. So that is a piece that people missed, and unfortunately, since there was not enough participation in it.
Wait, Vivek. I think I won't miss because inside the recursion I am running a for loop as well on the whole string length. So in one case, can I type it here? So,
yeah, go for it. Yeah, you have access. Yeah, go.
So in the one case, in next cycle, okay, my string will become like this. But because I am running the for loop in another cycle, when it is returned, it will be sent as this.
Got it. And then you will actually be sending PP in both cases,
PP,
right?
yeah.
Sweet. That's exactly what I didn't check your code deeply enough to figure it out, but that's the thing. I mean, it so happened it worked, which is a good thing. But that was a trick in this question.
Got it. Yeah. Because I understand. Yes, this was a trick, but I didn't thought about this condition and created that for loop. I just was like, okay, I was iterating that. Okay, if I find, but yeah, my thing would work.
Okay, so now let's talk about the try solution. So, Vikas, can you walk us through the try solution again? Because I think I have a concern with the try solution in general. So you start with hen, is it?
Yes.
Okay, and then what do you do? You start with H first, is it?
So we have all the words, right? What are the words hen and happen?
We don't have the other one. We have all the words, but your dictionary contains hen, your dictionary contains happen, it contains 1,000 other words. But go on.
Yeah.
So we put both hen and happen in the try.
Right.
And then we start with the first H. And now we have like in our recursion we have a state. The first state is A. First A, right? So A,
right.
And remaining match is APP.
So
from H, we look forward if there is A. We look forward by one.
But you could, if you had this, right, A, H, P, P, E, N, if that were a word, how will you catch it?
Yeah.
So since that is also a word, when we are at A, we look forward by just one. And there's not another A in that case.
I don't follow. So what do you start with?
Oh yeah. I was looking for HAPP.
Yeah. So he was starting with the index I equal to 0 as it is, like.
Yeah. So that may not work.
Yeah.
So you have to think about how to do it. See, there is a try solution that exists, but the concern here is that there are quite a lot of ways to insert the letters APP, like in hen, right? Just hen alone, right? You could if I had to insert A, I can actually insert A in here in 4 places, right? So it can become A hen, or it could become HAEN, it can become HEAN, and it can become HENA. Okay, there are so many ways to insert this. Now, how many ways can I insert a P in this? Right? There are 1, 2, 3, 4 places I can insert P, or 3, 2, and 1. So essentially I can insert, so there's 4 places I can do this, and then for the next one I can actually insert in 4 plus 3 plus 2 plus 1 ways I can put in the other P. The next P I have to put is actually more, which is essentially again I have 3 more places, 2 more places. I mean it's n cube ish ways of actually making this happen. It's significantly large. The number of combinations that you have to generate, and I understand that you're using a try to eliminate it, but if I actually suitably give you a data structure which doesn't help, you will be exploring all combinations.
Second P and third P, the number of possibility will start reducing as we pick the first and second. Because the third can only come after the first two, right?
That's the same thing with this one, right? The A can come in all the 4 places.
Yeah.
But then the P can come in the P can come anywhere in so I can put like from A hen, right? It can become APHEN, or it can be AHPN, or it can be AHEPN, or AHENP, right? There are this many combinations. So 4 ways in which it can happen, and the next one is 3 ways, 2 ways, and 1 way. Now, for this guy alone, right? If I want to add the next P, it can be APPHEN. It can be APHPEN, APHEPN.
Hear me out first. So in the try, we are looking for what state we are in. Initially, we are looking for A to eliminate without moving forward in the try. So let's say if the word was AHPN, we'll see an A right up front and we'll move our straight to P. And now we are now looking for P without moving forward. So that's the logic.
But if I suitably, I get it. If there are no words beginning with AP, then you will not even go downwards, right? I hear that. But my concern is that if I can suitably give you a data structure where all these words exist, except that like this word exists, these words exist except the last digit, right? Last letter. You will go through the entire try. You will enumerate the entire tree.
Right. Yeah, if you're saying the same, only the last is, then you have to keep going.
Yeah, and I think so. In an algorithm, right? You're trying to figure out now that I know your algorithm, I can actually engineer a data set which actually will make your algorithm work the hardest. Right? I can say these are all the words in the dictionary without the last digit, which essentially will make you go all the way down in the try without giving up.
Right.
Yeah, you can go do that. But in case of like which Vivek said, in the reverse case, you just have to eliminate it. So elimination and if
elimination is only one way, right?
It's only one way, and that too you will eliminate only if you found it. So your cycles and all will be very less compared to try. Because you remember I was also thinking of, once you said try, I was also thinking in that way. But then when
I think as soon as I heard the reverse way, I felt that that's so easy. That's much easier to do this way. No complicated structure, just put it in a hash and compare.
Yep. And the one, so 2 aspects here that I think I want to make sure I reiterate is that number 1 is that you could have multiple A's and multiple P's, so you have to figure out which A's to pick and which P's to pick, right?
Yeah.
And I think the algorithm, somehow your algorithm Kavit had it, so which is good.
Yeah,
but that is something to remember.
I tested it out also with this input, it works, so I was okay.
Now the third thing, in addition to that, the second element to actually figure out is that it is possible that you may actually end up with like sort of duplicate states depending on like which P you pick. Right?
Okay.
So for example, if I have a word which is like this, right? XYZP, right? Now if I this essentially, and the other word in the dictionary is A, B, let's say this was the A, one of the P's, and this, if this is how your thing was, right? So the second word in the dictionary was A, B, P, X, Y, Z, that's it. Okay?
Okay.
There is no difference between this sort of a capitalization and this sort of a capitalization. Right?
Yeah. That's
it doesn't matter which P you pick.
Got it.
Both will result in the same value. So you need to make sure that you are not double counting.
Yes. So that's where a double counting. I did something with the map, but I don't know if it worked. I'll have to test it with this input.
Yeah, try this input and try it out if you actually did. So these are the 2 gotchas in this question. One is the fact that there could be multiple A's and multiple P's, and the second thing is that you may have a scenario where you may have multiple P's and you have to pick one of them. They are like specifically they're contiguous. Then you may choose which P you pick will not make a difference to the output. So I don't want you to print it twice.
Okay, yeah.
Right, that is the only other thing. Right, so any concerns?
No.
So regarding that one, there can be a scenario where it can come up similar word from different word, removing the APP, the duplicate scenario. So I was thinking maybe like creating another set of output or something like that.
Yep. So what Kavit's algorithm was that he was actually trying to not only create a duplicate set for output, he was actually storing all intermediate states. So if you ever see the same intermediate state ever, you will just chop it and go on, which may be superfluous in terms of storage, but it got the job done. But you may want to revisit that to see if that is the right approach. Okay?
Yeah.
All right. So moving on to the third question. Is the appropriate package picker question. So appropriate package picker is essentially you are given n packages, and this is essentially you assume that the postman or the delivery person starts at 0. Okay, every packet has a weight and every packet has miles from origin, which is like essentially just a linear one direction, that's all. So the way it works is you want the package, the delivery truck has a capacity of C, load the capacity. So if you in trip 1, you will say I will pick package 1, package 3 and package 5 or something like that, and that's it, that's all I can take. In trip 2, I will pick package 2. In trip 3, I will pick package 4. So in 3 trips, I will make it happen, right?
Yes.
What is the cost of trip 1 is actually the longest distance.
Yeah.
What is it in each, and the total trip cost is this. So if you suitably reorganize your trips, you will actually get a different longest total distance traveled, and your goal is to minimize that. Does that make sense?
Yeah.
Vikas, does that make sense?
Yeah, makes sense.
And Manish?
Yeah.
Awesome. So that's the plan, right? Now how do you go about solving it?
Anyone wants to say their approach? I'll say then after that.
Yeah, Vikas, go ahead.
I did not try it, but the way I will try it is sort by distances first, and then pick the longest distance and put it in one truck, then pick the second one and put it in the next truck.
Why? What if you're able to deliver both in the same truck?
Yeah.
Oh yeah, then.
Yeah. So.
Oh.
Okay. So what I did is I tried it by a greedy algorithm. So suppose let's take a scenario.
Maximum distance we can deliver per weight.
Yeah.
So greedy not equal to good in general.
Okay.
Yeah.
Okay.
60 over here is the weight or the distance.
What is that again, Manish? Can you repeat the thought?
Oh, the truck's capacity is like a weight.
Yeah, weight.
Okay.
Okay, so
I think
because
I think the problem with the greedy is the partial truck full. So when we go by distance by weight, what if the truck has spare capacity and we can still fill it with less length?
So I'll tell you my approach. Wait, so I'll take an input as an example. I'll take an input as n is equal to 3, capacity is equal to suppose 23, and suppose package 1 value is, so first one is W, so W is 10 and distance is 2, and then package 2 is 20,3 suppose, and package 3 is 5 and its distance is 6. Now what I'm doing is I'm sorting it by weight. So what will happen? How it will rearrange in an
20, 10 and 3. 20, 10 and 3. 20, 10
yeah,
and
20, 10 and 3. Yeah. And
organized.
Yeah. This way. Now what I'm doing is I'll iterate. Suppose I is equal to 0, so that is at P3. Now till the time I reach the capacity equal to 23 or greater. As soon as I reach the greater than, I'll stop. So what will happen? I'll be able to calculate 5, then plus 10. That is 15. Now as soon as I add the next weight 20, it's above my cap. So what happens? That 15 is there. So I'm keeping the max, like, because P3 and P1, what is the max distance between them? It's 6. So obviously, even though 10 is at 3, 2, it's less than 6, it doesn't matter because I am carrying it in one trip. So 5 and 10 is 15 weight, 6 is my distance. So 6 going and coming back. So total distance is 12. So that in one cycle, my distance covered is 12. Now in the next one, my I will be at 20, P2. So that 20 is less than 23, okay, and then because the packages are over. So my distance traveled in that case scenario will be 3 plus 3, 6. So my total distance traveled is 18. So this is how I calculated. So I don't know if it's correct or not, but yeah, I'm taking it by weight.
This is a greedy approach, right?
Yeah,
so,
this is a greedy approach.
Yeah, so generally, so this is actually a knapsack type problem.
Knapsack type. Okay.
You need to know. So one of the things is with interview practices, right? You need to start kind of picking out the category of the problem and see what category it is. It's not the same knapsack, but it's a modified version of knapsack. It's multiple knapsacks essentially.
Oh, okay.
Right. So what is a knapsack? Is essentially you sort it in some order. It doesn't matter which order you sort it even. Is that what you're saying? Is that if let's say you don't sort it, right? You have it in any random order. So
okay.
your trip 1, right, will contain P1. Let's assume that the optimal solution, trip 1 will contain P1. It doesn't matter, the order of trips is not relevant, right?
Yeah.
So your trip 1 will contain P1. Now what happens to P2?
P2 cannot be accommodated to in trip 1.
In this example, you cannot accommodate P2, but there is a possibility that P2 could either be accommodated in trip 1
okay. Yeah.
or P2 is actually a part of trip 2.
Okay. Yeah.
Those are the two possibilities, right?
Yeah.
What about P3?
Again, P3 could be in trip 1
and
it could be in trip 2 also alone.
Yeah.
And trip 3.
Or it could be this, right?
Yeah.
And so on. And then at any point of time, if P1 and P2 are like, capacity is going over, then you don't calculate the rest of the part of the tree anyways, right? This is a standard knapsack.
Yeah, it's a standard knapsack. Yes.
Can you repeat how is standard knapsack?
Are you familiar with knapsack algorithm, Vikas?
Yes, I'm familiar.
Okay, so essentially what I'm trying to do is this, right? So I'm saying P1 is a part of trip 1, always.
Okay.
Okay, now what can happen to P2? Either P2 is a part of the same trip as P1 or it is a trip of its own, correct?
Mm-hmm.
Those are the two possibilities and I'm going to actually branch out at that point of time. Okay. I will solve with P1 and P2 being the same trip and I still have to figure out the rest of them, or I will solve with P1 and P2 as two different trips and solve for rest of them. So you will have a scenario where you may have P1 and P3 as one in trip 1, P2 in a separate trip. I mean, you will actually get all combinations is what I'm saying.
Yeah, combination, like you can think about it as a combination.
Like step 1, right? Step 1 is essentially I just have just P1, that's it. Step 2 is actually I will have a scenario where it's P1 and P2 in one trip, or I'll have P1 and P2 as two different trips. Okay?
So in knapsack we have a remaining capacity and remaining elements, right? A standard knapsack. So we have a total capacity, and assuming the last thing we put in is Pi, so we are left with a smaller problem with total capacity minus the weight of ith element, and then we have to maximize the total sum of Pi's in the and it's in remaining.
It is the same story here, right?
Okay, so what is the total capacity?
But you're not maximizing you're not optimizing the value here. What you're optimizing is the distance. So the equations, the math is completely different. But you have to think of it like a knapsack. Like why are we doing the knapsack steps?
Mm-hmm.
the same concept applies here. So essentially you are trying to generate all possible combinations of how to solve this, right?
Okay.
And as you solve this, you will actually have answers to what is the best solve given this current state,
Okay.
and you will memorize that.
Yeah, so it's a memorization process. So start with,
It is kind of like knapsack. It is kind of like breaking out this. So anyway, Manish, does that make sense to you?
It makes sense. You're basically trying to shuffle out sort of all combination and try to see which pieces fits those where sort of.
So the way of actually doing that is in terms of like I'm generating all permutations of how the weights can split itself. That's one, and then then I'm trying to figure out like at some point of time it is like knapsack like, because once I know the solution for a subset of the problem, I can actually apply that to the Uber problem and see which one's the minimum value. So this is an interesting solve. I think if you haven't done it, you have to write the code for it to actually make it work, because this will make sure that you can actually, if you understand knapsack the right way, then you should be able to write code for this. If you have only superficially looked at knapsack and you kind of know the general direction, then it will be hard to map your knapsack concepts to this. So this is going to test your assumptions and understanding. I like this question. So again, this question is something that I had come up with as well. So I don't think I have seen this question anywhere or an equivalent question anywhere.
Yeah.
So isn't generating all the permutation with the n factorial complexity on this one?
You will not be generating all the permutations, primarily because the problems you may end up generating all the combinations, but at some point of time you will actually notice that the problem is will actually solve itself, fit itself, because you are actually, you don't have to generate all the permutations, right? If you already have exhausted all the current trips and you need to find a way to actually, you are left with say P3, P4 and P5, and you are left with so much capacity, you know how to solve it because you have just computed that before.
Right. Yeah, that have already been ticked here, so that
Sort
wouldn't be picked up again.
So that is why it won't be n-factorial. It might very well be, like given the data set is so unique, right? If I give you all like Fibonacci series numbers in P1, P2, P3, 5, right? I think that will end up being, you will have to generate all combinations to see which one actually works. There are a few optimizations you can do, is to by actually sorting it in the weight order, so that a weight order or distance order, you have to pick one sort order and see which one works. And then what it does is that if your current solution is actually exceeding the best known solution so far, you can actually start ignoring it. So that way, there are a few tips we can do where we can actually easily kill out a bunch of things. So there are, I think you'll have to think about how to make this work. I mean, this is essentially taking the knapsack-ish algorithm and then translating it to this.
Yes.
This may be more closer to bin packing. Like if n is
actually, this is bin packing. This is actually bin packing. Knapsack is not the right answer. Sorry, you're right.
Okay.
They are similar in the fundamentals.
Yeah.
But at the face of it is bin packing. Like I was thinking when I was imagining this question, and I was thinking more like knapsack, trying to see how to fit. But I think this is actually I think this might be the bin packing problem itself. Let me see.
And for bin packing, the offline decreasing next fit or decreasing best fit, those kind of approximation algorithm are logarithmic, but
no. The only difference here is that in bin packing you're trying to minimize the number of boxes, right?
Right.
And here you're trying to not minimize the number of boxes, but actually you're trying to minimize the value of the maximum. So it's kind of like bin packing, but the cost vector is actually different.
Yeah, cost vector is different, definitely.
Yeah. So I was actually trying to solve it like knapsack, but you're right. Maybe that I'll have to think about it. But anyway, I think you have the direction to move forward, right?
Yeah. I'll try. I'll think more.
This is definitely worth trying. Please feel free to paste the code after you've done it. It's always helpful to discuss.
Yeah, I just saw this question actually.
Yeah, this is a good question.
Yeah.
Yeah, I'll try it with knapsack and I'll try to post a solution. Yeah, because my one is greedy one.
In the channel.
Was that Manish?
Oh, sorry, I interrupted.
Go ahead, Manish.
Yeah, I didn't see this question in the channel. I just saw this question, so yeah.
Yes, I did not post this question because people didn't want it. Anyone who asked this question, I actually privately messaged them.
I see.
It was only Vikas and Kavit who had asked for it, so I had sent it to them.
Cool. Yeah, I'll try this. It looks very interesting question.
See, so anyway, and then the next one is the last one is essentially arithmetic path problem.
Yeah.
Which is what? Like you're given two prime numbers, you're supposed to print a path from the first prime number to the second, and you are only permitted to make an edit distance of 1.
Okay, yeah.
So how did you go about doing this?
Okay, so again I used sieve. So I had all the prime numbers, suppose at 2, 3, 5, 7. Okay, so that's all generated. That's done. Okay, now I iterated like for all, like for 2 to all the primes calculated. So I took the pairs 2 and 3, 2 and 5, 2 and 7, and I calculated the edit distance. So I calculated the edit distance by converting them to first string. So I converted 2 and 3 to string, and then I recursively calculated either they could be formed using either by adding one more letter, either by removing another letter, or by replacing. So then I got all the edit distance as 1 for 2,3 I got 1, 2,5 I got 1, 2,7 I got 1. So then I created a graph with 2 to 3. Then I created another graph 2 to 5. Then I created 2 to 7. Similarly 3 to 5, 3 to 7. Yeah, it will go on. Now once I have graph, what I did, I started a BFS.
Right.
And
so this is a classic question which combines 3 different fundamental concepts. Right?
Yeah.
So fundamental concepts are: number 1, how to figure out prime.
Yeah.
Number 2, how to figure out edit distance of which numbers are actually linked to other number.
Yeah.
So you generate a graph, you create the base or edit distance of 1.
Yeah.
And then the third step in your puzzle is to do the breadth first search.
Breadth first search, yes.
Right, because you're trying to find the shortest path.
Yeah, shortest path. Yeah. DFS kind of could be worked, but it would take a lot of times because I would recompute the same path and like.
No, DFS is a terrible plan, right?
Yeah, terrible plan. Yeah.
Breadth first search is the way to do it. Whenever someone asks a question of saying shortest path, that is what is the thing. So that makes sense. Now, one thing you may want to think about is whether you want to actually calculate the edit distance as your second step. Like you can dynamically generate the graph instead of statically generating it. So you generate the primes first.
Okay.
You start with the first number.
Okay.
You compute the edit distance of all the prime numbers that you have from the first number. Like all the other primes are from the first number.
Yeah, I did that. Like
sorry to interrupt.
Yeah. Go ahead.
Can you explain the edit distance concept here?
Sure. Edit distance, it's the thing is called the Levingstein's edit distance. It is what it is that it actually the edit distance is the number of transformations you can perform. You need to perform to translate one string to another. Okay. And how it actually works is that the most common, like edit distance is the edit, and there are like rules around what those relationships are. So if you go to the wiki article, it actually tells you, so you are permitted an operation of one insert, one delete, or one substitute is considered like an edit distance of 1. So if I have a number like say 1 2 3 4 5, right? 1 3 3 4 5 is considered edit distance of 1, because what did you do? You just replaced 2 with 3, right?
Oh, I see.
Okay. What about this one? What is the edit distance between these two?
I mean, you kind of reduced by 1 with 2.
Edit distance is 2 because you can delete the 2
Mm-hmm.
and then you can insert a 1 here,
Yeah.
and that's it. The edit distance between 1, 2, 3, 4, 5 and 1, 3, 4, 5, 1 is actually 2.
Yeah.
Okay, and so on. So that's the concept of this. So here edit distance of 1 essentially means that the two numbers have the difference of one number, like either you have a one letter substitution, one deletion or one insertion.
Okay. So basically, I think you can just pretty much sum up all the numbers and see the difference is, absolute difference is 1.
No,
I don't
what do you mean? No.
know. Oh, that won't work.
So no, not at all, right?
No, the absolute difference is like huge, like it's by 1,000 something.
No, even if you sum up all the digits, right? That won't help. Like this could be a 9. Still edit distance is only 2.
Yeah.
Yeah.
I mean, the part where you can delete part. If it was just add or subtraction, then that might work, I think.
No, the edit distance is the edit distance is a separate concept of its own. It is a problem of its own, where it's actually a dynamic programming problem. And how to calculate the edit distance, like check out the Wikipedia and check out like write code to actually compute the edit distance. It's not a super hard problem to solve, but it is something that will actually, it'll blow your mind in terms of how it's actually done, based on like how you're actually trying to minimize the cost and things like that. So it's a fun little thing. I think we've done it in the Seattle Tech Interviews meetup at least once before.
Yeah, cool. Yeah, I'll definitely.
Yeah, edit distance is actually used when you do Google search to do spelling corrections, like the word which is closest to what you typed. They use the edit distance in the dictionary to give you a suggestion that maybe this is the right word you're looking for.
Yeah.
I was thinking of one more thing. So instead of checking, so when we are generating this PFS dynamically, instead of checking against all the prime and taking their distance with the current number we are in consideration, that will be order number of prime. So instead of that, take the number, generate all one edit distance number from it. So that will be number of digits in that number and how many options we have for every digit for replacement, adding, or deleting. So that will still be bounded by number of digits time, number of options for every digit. This won't be unbounded. And then check if the resulting one distance number is part of your set, prime set. If it is part of your set and you already haven't considered that in your BFS, then you add a link, outgoing link to that, to include it in graph and add it to your BFS queue.
Yeah. So I was also thinking. No, fantastic. So let me take a step back, right? So one thing to note is that edit distance is a concept of itself, and computing edit distance is actually a more involved process. But if you need to find out if two strings are actually of edit distance 1, right? Yeah. That's a much smaller problem because you can abort immediately after you have discovered a larger edit distance.
Right.
Right. No, and that's exactly what you're doing here in some sense, because you're looking at actually I have a 7-digit prime number, so you're only checking for all like 7-digit prime numbers with one substitution, or you're looking for all 6-digit prime numbers with one deletion, or you're looking for all 8-digit prime numbers with one addition, right?
Right.
And that's essentially like a simplification of the edit distance mechanics. But at the end of the day, you can actually achieve the same thing using the edit distance recursive formula, where you're actually adding a break condition of where you're going more than one. You can do that.
No, this is not what I'm saying. So assuming that we have 1 billion prime to consider, but for every number, I don't need to compute the edit distance with all the other billion primes. What I can do is, given this 8-digit number or 10-digit number, I create all the 9-digit or 11-digit numbers with edit distance of 1 with this number. So
you also need to include the same length also.
No, not really, because 10 digits for every digit I have 10 replacement choice, so that's 100. And then if I delete or add, then I have 10 choices. For each choice I have 10. So it will be like 1,000 choices, not billion choices.
No, that I understand, but I'm saying, okay, you're trying to eliminate it in some form, but all I'm saying is that if you were to consider, like, edit distance itself is a simple bounded question where you can actually write your function which says, given two numbers, can you tell me if they're actually edit distance of 1, and that can be solved in O of D time.
Yeah. So I'll tell what Vikas is doing wrong is, because I suppose what he's trying to do is, if he's taking a number and if he's trying to generate all other numbers with distance 1. So suppose for each prime number, as he said, like, it could take 1000 or something, 2000. So suppose if there are like 100 or 200 prime numbers, so 200 into 1000, like, itself the computation is like very big, and as Vivek is saying, it's very difficult. Like, it's not a smaller problem. You are trying to generate another new form of number with the edit distance 1. That is itself would be a very complex stuff. Like, writing a function would take time also, and the computation would also, I don't know.
I see. Sorry, I completely misunderstood what you're saying, because thanks, Kavit. I see now what it means. So the two options you have is, one is either to look at the prime numbers and check if they are with edit distance of 1 from the source, or you can actually generate all numbers of edit distance 1 and then check if they are prime numbers, if they are the prime number set, right?
Yes.
So you can do both operations, and I think the operation of actually starting from the prime number and checking it for edit distance is a faster operation than the other way around.
So generating all the numbers and checking whether they are part of
No. So you have two options. You have, like, start with n, and then you are saying that I will generate like all numbers which are of edit distance 1, and then you will check for prime, right? This is option 1. Or you essentially start with n, okay? Then you actually just explore the set with n minus 1, n or n plus 1 digits, right?
Mm-hmm.
And number of digits based on this, and then check for edit distance of 1.
Yeah, I think
you have two options.
Yeah, second approach seems, I think, might be a little faster than the first one.
Yep, because the second approach actually is well bounded, and checking for edit distance is actually is fast, and the number of elements that you actually have here is actually fewer.
Because they have already generated the prime numbers.
I think that will be a subset. You're right.
And here it's a set lookup. So this step is fast. Like, so this step, right? So A1, A2, A3. The A3 step is actually as fast as B3.
Yeah.
But
so,
you will be generating the A2 size is more than B2.
Yeah, I think I missed the point that we only need to check primes which are 9-digit or 11-digit or 10-digit. And
for edit distance, right?
Yeah.
For edit distance. Okay, got it.
Yeah.
Awesome. So that's it for the questions. So what do you guys think?
So one more optimization on this is we can start BFS from both primes together, and at some point the two BFS set will intersect, and that will be the shortest distance.
I have not seen that kind of an approach actually. For how is it algorithmically more efficient than starting from a source and going all the way to the destination?
So if you start from only one prime, think of it like a circle. The circle will keep expanding. So the area of the circle, if the radius is r, the area of the circle is proportional to r square. But if you have two circles, the area of two circles will be r by 2, and it will be proportional to r by 2 square. So
interesting.
R by 4. So
interesting.
Less time.
Interesting. I like that concept. Does it make sense?
I'll have to see. I'll have to take a paper pen.
No. Look at it this way, right? If you have a point in two-dimensional space, okay?
Okay.
And you have every point connected to every other point.
Yeah.
Okay. Now, when you do a breadth first search, right? What are you doing? It's actually like it expands as a circle, right?
Yeah.
Like, so it expands as a circle. Now, as you're going bigger and bigger, you are actually making a circle bigger and bigger.
Okay.
Right? So now what you're doing is that at the point of final stage, your circle will be as big as the distance between the 2 points, correct?
Yeah.
Instead, if you actually apply the algorithm of where you are making the circle actually spread from both points.
Oh, okay. And
At the time of intersection, you will have two circles of half the radius.
Got it.
Right? That makes sense?
Yeah.
But okay. So but in case of like in terms of code, like what will be the intersection thing look like? Like I have the BFS as 2 then 3, and then for 3 again it's 3 and then 2.
So
right?
the way I look at it is that what you will do is that you're adding queue, right? Instead of having one queue, you'll have two queues, right?
Okay.
And you'll do level hour traversal of Q1 and you'll do level hour traversal of Q2. You do that. Once you're done with it, then again you have like fresh Q1 and a fresh Q2. You keep going. But instead of throwing away all the elements, you keep all the elements in a set.
Got it. Yeah. Now I understand. Yes.
So that way, if you find an element from B which is actually in A, you have found a match point.
Match point. Got it. Yeah. That is already visited. Okay.
Correct. And if you just like visually look at this, it's very obvious, right?
Yeah, it's very obvious. Yeah. Now because it's like 2 points and two people are starting walking to each other.
Correct. And then the area of the circle covered actually is much lesser. If it's two circles of r by 2 radius, the area is obviously much lesser. Than one circle of essentially r radius, right?
True.
It's around 1/4 radius.
Yep. Awesome. This is so again blew my mind. I hadn't actually thought of it this way. Fantastic.
Yeah.
Great approach. So fantastic. So what we'll do is I think we'll stop here. It is 8. So let me turn off the recording, and then I will upload this in YouTube, and then I'll share the link in our private chat so that we can, because if you want to like rewatch this and see and revisit some concepts, please feel free to do that. All right?
Yeah.
Awesome. Thanks everyone.
Thanks very much.